back on YouTube. Okay, so go to new worksheet. Name it LAC03, the third day of Life After Calculus. Yes, there is Life After Calculus. We're going to be doing DiffEqus. What's that? Differential equations. Put your name in here somewhere. Put the date. Oh my God, it's June. Okay. So let's do some DiffEqus. Let's start with some easy ones that we know already. Remember variable separable stuff? Let's see if we can do that stuff on a computer algebra system. Here's a variable separable equation that you should know well. Y prime, or dy dt, is proportional to y. Let's say. Do you know what kind of solution curve that would give? Do you remember? No? You don't remember? Let's make it more obvious. dy dt, how do you variable separate that? This is just a comment. I'm not doing any sage yet. How do you variable separate that? dy over y equals 0.2t. So when you anti-differentiate, you get dy over y is integral ln y. What is this thing? Well, ln of y. I want y. E to the. Isn't this exponential growth? Yes. This is exponential growth, so I'm not even going to do that. All right, so let's see if we can make Sage do this for us. How about a slope field? How do you do slope fields on here? Let's see. How about if I say, oh, let's see. I have y's running around, don't I? All right, so I have the var y. Remember var y? What's that about? Y is usually just a numerical variable unless you tell it it's an algebraic one this way. So there you go. All righty. And hang on to your hats. Ready? Plot, vector, field. This command is really not for slope fields. I'm sort of forcing it to do slope fields for me. It's really a vector field, like when you have gravitational well, a potential well, difference in voltage, potential, electric field, magnetic field lines. You can graph stuff like that with this. But I'm going to cheat, and I'm not going to graph vectors of magnetic field lines. I'm going to graph a vector where wait, listen, shh, excuse me. I'm going to graph, remember we did slope fields? On the T89, it would make little line segments that were sort of like pieces of tangent lines and sample all throughout the screen so you could see get a feel for what the solution curve would look like, right? Well, I'm going to do something like that by plotting little vectors. Are you ready? My vector, each of my vectors will have an x component of 1. That's not interesting. And a y component of 0.2 times y. Why? Because I'm solving this. Okay? Alrighty. And let's say, okay, I have to tell it the domain. Let's say x goes from 0 to 10. That's how you write it. The syntax for plot vector field is weird. And let's give it a range. How about y goes from 0 to 20? And that'll do. And there's your slope field. Now, does it look exponential? Does it look like if you have an initial position like 0, 0, 1, and you graph along these slope lines, you get an exponential growth curve? Yes. The only thing is that these lines are not all the same length. I should probably normalize this. What's the length of each vector? How do you get the magnitude of any vector? Pythagoras, right. So let me Pythagoras. How about if I call it L for length equals the squirt, what? What's that? Square root of the x component squared dx dt and the y component squared dy dt, right? So let's say 1 squared is 1 plus 0.2 squared is 0.04 times y squared. And let's divide each of these by L. So it looks like a real slope field. Each slope line should be the same length. Now, Yeah, I guess so. They're all the same length. They're all unit vectors. All right, do you see what I did? I normalized each vector. Each one before was a little bit different length. They got bigger and bigger, longer and longer. Now I normalized them. I made them all the same length by dividing every vector by its own magnitude. So these are all really unit vectors, okay? Now, don't worry about the arrows. The arrows are there for electric field lines or magnetic field lines. We're not doing that. So just think of these as little line segments. Doesn't that look like a slope field that we've gotten before? It doesn't look like that? All right, who's stuck? Coming around. All right, so this is a vector field, not a slope field, but that's okay. So who's stuck? Yeah. Okay, and what I did was I took that L, the length of each vector, and I divided the component there by L, divide by L, and then divide this component by L. So then these are all going to be shorter. See? It just makes it nicer. That's all. You don't really have to do that. All right, who's stuck? Who's stuck? Who's stuck? Who's stuck? Who's stuck? Looks okay. Looks okay. Looks okay. Yeah, that's weird. This is a 1. That's a 1. That's an L. That's an L. That's an L. That's a 1. It's slightly different font, but not that much. This is 1. This is 1 squared plus 0.02 y squared. Square rooted is the length of each vector, right? Divide each component of the vector by L, you get a unit vector. The 1 divided by L and stuff divided by L. Okay, good? Everyone okay now? It just makes it look like a real slope field. The lines shouldn't be, different lengths. You don't have to do that, but it makes it look better. Okay, can I see your slope field? Mm-hmm. Okay, so everyone divided by L, we're good? Everyone okay with that? Okay. All right, so that's an exponential slope field like we expected, right? Exponential growth. Okay, let's do another one that we're familiar with. Well, because L is the length of each vector, so if I divide each component by the length of the vector, I get a unit vector. Each vector is still pointing in the same way it was, but now it's only 1 unit long. Alrighty, so let's do the same thing with, let's say, remember Newton's law of heating and cooling? Let's do one like that. By the way, I call this 1A because there's going to be a 1B. Hang on. Here's 2A. 2A. Let's put in, this is also variable separable. Let's see if you recognize it. Y prime, or dy dt. How did I write it up here? I wrote dy dt. Or I'll write it that way here too. So dy dt equals, is proportional, there's a constant proportionality, to room temperature minus current temperature. Remember this? Isn't this Newton's law of heating and cooling? Let's see if we can get a slope field for this. All right, let's see if we can do it. How would you do it? Plot. You tell me. Just like number 1. Plot. Vector. It's underscores there, right? Vector field of. All right, now I'm cheating here. I'm just going to make the x component always 1. The y component is the y prime. So 0.2, remember multiplication, it must be explicitly written, times the quantity 100 minus y. I still have a var y from cell 1, so I'm okay. And let's see. Why do I have, yes, that's right, okay. Comma. Let's say a domain for x from 0 to 50. Comma. How about the range for y is, I don't know, 0 to 200. Whoops, what'd I do? Whoops, what'd I do? What'd I do? I did something stupid. Wait, hang on.
There we go.
Vector.
Very crazy.
There it is, okay. And, all right, do you see it? Now, does that look like a cooling curve or a heating curve? Approaching the ambient temperature, 100? You want to do the L thing again? Sure, why not? Let's make L, the length, equal to of the x component squared. 1 squared is 1. Wait, the squared of this, Pythagorized, right? 1 squared plus that other thing squared. What is that? 0.04 times 100 minus y quantity squared. And then divide each component of those vectors by the length, and you'll end, because I'm squaring it, right? The component squared, and divided by L, and let's see how that looks. That's a little better. Nice slope field, yeah. Okay, everyone got that? Wait, no? Who's stuck? Bueno? Okay. Oh, it's not coming out? Okay. Well, you're probably just missing a parenthesis or something crazy. Let's see if your L is okay. Yeah, close parenthesis with the square. Try that. See if that's all it is. And that's all it is. Yay. All right, so that's a nice little slope field for Newton's law of heating and cooling. Depending on your initial conditions, you'll be heating or cooling. All right. We're going to solve this analytically, too, and we're going to graph on top of the slope field. Hang on to your hats. You're stuck here? Yours looks weird? Okay. That's your range, I think. Hang on. All right, well, I don't see anything bad yet. Well, wait, you got too many commas. It's L, it's 1 over L. Is that a 1 and that's an L? 1 over L. Right, and then you have too many zeros here. And too many commas. Okay. And it's that thing's, what is it? It's point. Yeah, that's right. And, okay, here, this is it, okay. All right, let's see it. I don't want to see that. Looking good? Did you fix your range? It was a range, right? The Y max or something?
No, I have plus equals there.
Oh, that'll mess you up. Say what you mean what you say. You get some gobbledygook, you know? All right, what happened? Not good? Your squid looks good. Open. Yeah, you did that too. Where's all this coming from? It's 0.2. You had a 0, 2. That's what you had. Okay. All right, so that's all it is. Ta-da. All right, so remember on the AP, you were responsible for solving any variable separable, but it's specifically exponential growth and decay, Newton's law of heating and cooling, and logistic curves. Remember logistics? You know, the carrying capacity of the mongoose on the island? Yes, okay. It looks like exponential growth at first, and then it levels off, that kind of thing. All right, let's take a look. Let's see if we can get a subfield like that. Let's see, number 3A. Let's see, what's a good example for 3? dy dt is, well, this is still var sep. Variable separable. Okay, dy dt is, how about proportional to the current population and the people that are missing in your population. Yeah. This is how many people are in your population, this is how many people are not in your population, and this is how many people you get at most. Eventually you'll get to 100. All right, so this is just a comment. This is what we're going to graph. So let's graph it. Plot, vector, field of, let's see, open parentheses for the vector, 1. I'm just making the xct always 1 to make it easy. Comma, and, oh wait, I meant 0.01. Make it 0.01, okay? So 0.01 times y times 100 minus y. So this is still a first order differential equation, but it's not linear. What? Do you see what I'm saying? This is still a first order differential equation, but it's not linear. What does that mean? You're solving for y, right?
So I get something like this?
What did we say? Yeah, depending on the window, looked a little different, but it's a first order differential equation. In other words, it only has y prime in it. It doesn't have like y double prime, y triple prime. Third order would be y triple prime. Second order, y double prime. First order, y prime, right? But the function that you're solving for, y, if you FOIL this out, don't you have powers of y in second degree? So this is not a linear first order differential equation. This is a second degree first order differential equation. But we can still solve it. So let's close that. Comma, how about a domain for x from 0 to 10? And how about a range in y from 0 to 200? And now maybe we should normalize this, huh? Let's normalize it. The length of each vector is the square root of the x dt squared, which is 1, plus the y dt squared, which is, well, what's 1/100th squared? 1/10,000th. So 0.0001 times y squared times 100 minus y quantity squared. And divide everybody by L, just to make it look nice. Divide that by L too. And what'd I do? Oh, wrong slash. What am I doing? Oh my God. Wrong slash, forward slash for divide. And that's a little better, okay? So remember, logistic growth has sort of a concave up, then a concave down, and it levels off to horizontal asymptote. And logistic decay is sort of like Newton's law of cooling, really. And there it is. All right, so that's sort of how you solve differential equations graphically, right, if you can't do it analytically. But these are variable separable. These are very easy to solve by integration, right? Can we make Sage do that? Let's see. Let's go back to 1. I'm going to make a new cell down here called 1b. Everyone got this? Everyone stuck? Who's stuck? Everyone good then? All right. So now let me make a new cell for 1b. Now 1b, I'm going to do 1a, but analytically. All right. So in 1b, I'm still talking about the variable separable equation that says y prime with dy dt is equal to or proportional to y. And I'm going to give an initial condition. How about y at time equals 0? What? No. Period 4 ends, what? 11. So that's wrong, sorry. Let's say initial condition of y0 is 3. Look at the schedule. Period 3 ends at 10:11. That's the old bell. That was the normal bell. They didn't switch to the, yeah. We were on the homeroom bell? Yeah. All right, so anyway, so that's what I want to solve. So how do you do that? Well, this is how you do it. Ready? Yes, we know.
Please disregard the bell. There was a bell misfunction. Please disregard the bell.
Is that like a wardrobe malfunction? That was a wardrobe malfunction, yeah, okay. Misfunction. Well, yeah, I'm on YouTube, so I'm not going to say anything. I get into a lot of trouble.
Well, it's too late. The internet now knows.
The internet does not know what I was going to say. All right. Now, nothing? I know nothing? I said, no, I don't feel like bleeping out later. All right, so this is it. This is the problem. We're trying to solve for y. But didn't we var y before? We made y act like a variable. I don't want y to act like a variable. I want y to act like a function. So I have to say something weird. Ready? Y equals a function called y of t. This is weird notation, but I need it. Okay? All right, here we go. And now let me think here. All right, that's good. Okay, so now let's solve it. Are you ready? Now remember yesterday we used that thing Taylor? Remember Taylor? And I said there was a Taylor on the HAL. Did you know that? Well, I'm now going to use another function, DESolve, which, by the way, is also on HAL. Did you know? Differential equation solver. All right, so let's do it. DESolve. Now, hang on to your hats. What are we solving? We're solving the derivative of y with respect to t, the first derivative. Remember, diff means derivative. This means second derivative. This means third derivative. This means first. Okay? Isn't that what I have here? Y prime? That's what that is. Okay. Now, for dE self to work, I have to set this equal to 0. So how should I write it? Y prime? How do you set this equal to 0? Like, you know, quadratic equations? How do you set this, how do you make one side 0? That's the question. No. I want to move stuff to all to one side, so I have 0 on the right side. Subtract. So y prime minus, are you with me? What? Minus 0.2 times y. Right, okay. So dE self requires your differential equation to have 0 on one side, that's all. And let's solve it for y. Okay. Whoa. Oh, I didn't var t, did I? All right, you know what? Make it x. Forget that. I automatically have a var x, so make it x. Okay, there you go. Did you expect that? Oh, let's make it pretty. Print. There you go. Do you expect anything like that? Didn't we usually get a constant times e to the something t, right? Right? That's exactly what you expect. All right, what if I want to put the initial condition in? This is how you put the initial condition in. Ready? It goes, where the heck does it go? After the y. All right, so comma. And my initial condition was when x is 0, y is 3. So this is how you write it. Square brackets, 0, comma 3. And there's your initial condition. Isn't the initial condition of y of 0 is 3, isn't that usually the constant? If you plug in 0, you get 3, right? Yep. Okay. Can we graph that? Let's graph that. All right, plot. Now this is just a normal plot, not plot vector field, just a normal plot. What am I plotting? Well, I'm going to plot this. Ring. Just highlight it, Control C, then Control V. Let's say, let's see, now I'm forgetting what I'm doing here. Well, all right, let's see what that looks like. Invalid. Whoops. Yeah. All right. Well, that's not a good window, is it? How about if I say my plot, let me change my plot to go from x min. I think my x min on the slope field was 0, and my x max on my slope field was 10. I want to match them up so I can graph one on top of the other. Eventually, let's see. What'd I do? Oh, equals. There you go. All right, so there's an exponential growth curve where y of 0 is 3, right? Exponential growth, perfect. Now, here's what I want to do. I want to put this graph, whoops. I want to put that graph on top of its slope field. How do you suppose we can do that?
We can say plot something or other as one thing, and then plot.
All right, so name your plots, right? Okay, go back to 1A.
Cube equals plot whatever.
Right, go to 1A. Now 1A has the same domain, 0 to 10, right? So do this. Call this something like plot 1A equals. Now it's gone, right? How do I get it back? Show plot 1A, let's say. All right, so it's still there. But now I have a name for it, so I can use it somewhere else. All right. So I'm going to go down here, and I'm going to call this plot 1B, and I'm going to show, guess what I'm going to show? I want to show both. So, what do you think? Plot 1A plus, actually, plot 1B. All right. All I did in 1A was instead of showing this, or this being the last line, I named it P1A equals, so I could show it here, and I could show it later. So I have a name for it, so I don't have to redo it. Okay? So it's sort of nice to see that your exact solution matches your slope field, which is just an estimate, a graphical numerical estimate. All right, so this is still the slope field. I just gave it a name, so I have to show it to see it. That's all that's new. Right? You got that? But now I have P1A available down here too if I want it. Where did it go? Right? So I named this plot P1B so I can graph both of them together on the same domain, and it looks nice. So there you go. So you got that? So I want to do that with all three of them. That was 1A, 1B. Let's do 2B. All right, who's stuck? All right, no problem. Yeah, we got shortened periods today, so if we continue this on Monday, that's fine. And yeah, that's just a slow connection to the internet. So if you save and quit, and you open it up again, it hopefully will reevaluate it. And let's see, which one? That one, right? Yep, good. All right, what, you're stuck? You called it Q, you called it Z, and did Q plus Z, that's right, but T is not found. But you have a T. T's right in the beginning, right?
Yeah.
What the heck? Wait, let me see this.
Because Q works, I know that.
T not, why is T not found? You var T here. Are you doing something weird to T somewhere else? No. Interesting. Oh, you put it all in 2A. Wait, you're in 2A or 2B? I'm in 1. Did you get 1 to
I
work?
noted it differently.
Oh, you know? Okay. So this is really my, that was my 1B actually. But anyway.
It's just, the first ones were just 1A, 1B,
Yeah.
1C. Next ones are going
All
to
right.
be 1.
Oh, I know what it is because this is graphing in X. This is graphing in X,
Yeah, and the
and
other
this is graphing in T. So get rid of this. We don't really need it. And make it match X everywhere. Make an X there. And where else is it? An X there. An X there. Any other ones? Any other T's? Yeah. All right, try that. Is that it? I think that's it. Whoops, you did something crazy there. I don't know what you did there. All right, try that. No, it still doesn't like something. What? Down here. Was there something else we did up there? We have a var y. We had a var y, but it didn't say anything about var y being a problem, right? So, is anyone else stuck? Yeah? Well, this is going to take a while.
Save and quit, because here's about to end.
Yeah, we got about. I actually got 2 minutes. That thing's fast, but. Wow, I don't see it. See if we can look at it a little bit more. I'm going to go around. Who's stuck? All right. What did it say now? P1A is not defined. Let's see. That would be up here. P1A is there. You got to run it. After you change, you got to run this again. Otherwise, P1A doesn't exist out here. So maybe that's all it is. And it is. Yeah, that's it. Good. Okay. Is that your range doesn't match quite? What happened there? Are you going from 0 to 10 there? Are you going to 0 to 10 in 1A? No, I'm talking about the X's. Yeah, that's weird. I thought it matched up nicer than that. But all right, that's okay. Close enough. Who else is stuck? Me who? George? George is like massively stuck? What? Well, it's DE solve, not DI solve. Where's that DI solve coming from? It says DI? Where's that? You must have wrote DI somewhere. DI, DE.
What am I doing?
I don't know. What are you doing? Yeah, okay, you can save and quit. I guess we'll finish this up on Monday.
Wait, what about this?
What happened now?
What I talk about this?
Oh, up there? Unable to simplify float? What? Plot vector field. Let's see, is your squirt good? It looks good, okay. So it's quantity, 1 over L, 0.0 over L, yeah. Yeah. I don't see a problem here.
Oh, wait, here it is.
What?
That has to be 0.01. 0.01 this? It is 0.01.
Well, that's a comment, though. Yeah, that's a comment. It's not going to change anything, but you can fix it.
Which one?
Wait, this is a comment, but that's not going to help.
The first line is...
The first one is this thing squared, so 0.0001, y squared, yeah, that's right. Yeah, I don't see it.
What sense does that make?
Unable. All right, let's see if this helps.
Yeah, I was looking through that.
It's usually out here. What? We're not doing any kind of file.
It's a comment.
Yeah, that's a comment, so it's not going to matter. It is 0.01 because I made it 0.01. I changed that. I originally did have 0.1 there, but blah blah blah. That's right. Plot vector field of right that right. What the heck? Wait, something's really screwy here. Save and quit. Restart it. It's still doing it. That's really weird. These worked out fine, huh? They're basically doing the same thing down here, right? So what's different? It's not just square, because we would have said something around about L, right? So
Unable, like, what is it?
unable to simplify a flow. Save and quit, we'll fix it Monday. All right, fix it Monday if it's still stuck. Shh. Hey, you're on YouTube, stop. All right, so we're going to be doing DiffEqus for all next week. We're going to get to second order differential equations that you don't know how to do yet. Ooh, scary. Okay, YouTube. Bye-bye. Huh? Yeah. Oh, then there's paper on the side. You can load it. Why isn't it ending bye YouTube? It's not saying bye to YouTube. All right, bye YouTube. Bye YouTube. Bye YouTube. There you go. Boom.